Actually, you know what? I'm gonna have to do that for later. Sorry, I'm talking to myself right as you come in. This I don't need to save. Okay. Good morning, everyone. Welcome to our next to last lecture together. So we still technically have 3 more classes today, then Tuesday the 28th and Thursday the 30th. But remember, Thursday the 30th will be used for our final exam. So I don't want to give you a test on the same day I give a lecture, the final exam that is, because I'm only giving you 1 day, because I only can give you 1 day, as well as the only 1 attempt. But because I only give you 1 day, if the only 2 hours you have available that day are during the class, I don't want to make you unavailable to take the final. So that's just how things are done. Usually you don't give a final exam and a lecture on the same day, so I'm continuing that trend. It's just when I give you multiple days to take a regular test, I feel like I can lecture over that period instead because of that. Otherwise, I would skip lectures that day. Anyways, you have your homework due dates coming up, 4.5, the 23rd. I think 4.4 was the 21st. 4.6 is the 28th. We're going to cover 5.3 and 6.1 today, so they'll be due on the 30th. 6.1 is actually a really short section, surprisingly. The test only covers up to 4.5. Remember, I'm not going to give you any problems on 4.2. Now, in the review, now when I say no problems on 4.2, I mean using all the different little rectangles. In the review, you will find 1 or 2 questions saying to, quote, use geometry to find the area. And that's exactly like we did in the notes. It's just a line, so you use a rectangle. Excuse me, let me start over. It's just a horizontal line, which means you're doing an area of a rectangle, or it's the line y equals x or f of x equals x, which means you do a triangle. So you can see the notes from class for those, and I could still throw a problem like that on the test. I have no problem doing that because we lectured on that part pretty rigorously. Like what I said I won't throw on the test is having you make up like 10 or 50 or 100 different rectangles to estimate an area under a curve. The review, I believe I made 30 questions, which is a little longer than the first 2 test reviews. The first 2 ones were a little closer in length to the actual test. I think test 1 might have actually been exactly the same number of questions, test 2 a few more. But these problems, the integration stuff is a little, some of it's tougher, some of it's just the opposite of what we're used to. So I figured maybe a little more practice would help some students. Remember, you don't have to do the review. I don't count the review as a grade. If you get a 0 on the review, it doesn't hurt you. If you get a if you get a 100 on the review, it doesn't help you as a grade. It helps you study because the review questions and the test questions are similar. But please understand the test is not going to be 30 questions. It's going to be 17, 18 questions probably, something like that. Just enough to get all the material I want to see on it, but not having to repeat 3 different types of the same question. So you'll have 4 days for that test. It'll be Friday, Saturday, Sunday, Monday. So that starts tomorrow. It starts at 12:01 a.m. and then it'll run all weekend until 11:59 p.m. on Monday the 27th. If you do not have that test done by then, you've missed out. There will be no makeups for this. Final, the last little bit of the review is coming. Remember I said that the first 3 test reviews will make for a solid review of what material will be on the final exam. You won't really see anything on the final that I haven't tested on from the first 4 chapters, with the exception of 4.6. But then 4.6, 5.3, and 6.1, those will still be on the final exam because we will have finished the material in time. So I need to give you a small review assignment for that. I mean, it's probably going to be like 6 to 8 questions, maybe 10 if I want to get crazy with it, but it's going to be much shorter. And again, you'd need to study that in addition to the test 1, 2, and 3 reviews for the final exam. So I don't need to give you just a whole new blanket assignment. You can go back and do all the reviews. Remember that if you completed a question, you can always hit the similar exercise button and it'll give you something with different numbers, but the same basic concept. There might be like 1 or 2 questions out of those reviews that were multiple choice for something fun, and they might not be different, but that's not a big deal. It's just 1 or 2. And I really don't throw multiple choice questions on the test. So, that's more just conceptual review. Anyways, right? Right. All right, so if you have any questions about that stuff, per usual, email me. Besides that, we need to move on. Oh, I need a new page, new document. Get some enters in. Do. This will be 5.3. Improper caps. Improper integration. Now, you might be thinking, well, Mr. Beckner, what happened to 4.7? 4.7's numerical integration, that falls in the same category as 4.2, but worse. 4.2 is numerical integration, but just using rectangles. 4.7 is when we start doing other shapes like trapezoids, and it just makes for more complicated formulas, for more complicated examples, and then we're only estimating. And estimating is great if you can get accurate answers using computer technology and lots and lots and lots of those rectangles or whatever shape you decide to use. There are there are dozens, if not hundreds, of numerical integration methods just at our level. There are thousands of them at any level. So that's what 4.7 was. It was kind of an extension of 4.2 instead of just using rectangles. Like I said, maybe use trapezoids. We discussed how our rectangles were either anchored to the left or the right side. You don't have to do it that way. You can actually find a midpoint between those two and call that the height of the rectangle. So the left side of the rectangle might be a little above and the right side might be a little below. And a lot of people think that the midpoint version of that gives you a better answer. And I tend to agree as long as the polynomial is well behaved or the function is well behaved. And we kind of demonstrated that by averaging the left side approach and the right side approach. Now, the midpoint approach isn't exactly the same because of curves having changing slopes, but it is more in line with averaging a left side approach and right side approach. It's not exactly the same, but it's similar. It's less work, thankfully, but whatever. And then they have something called Simpson's rule, where they actually use parabolas to estimate the area under the curve. That is definitely the most complicated version of all of this. I would never, ever teach it in an applied calculus class. If I had a second semester of this, or maybe if this was a 4-credit class instead, we would go deeper into the numerical integration. We would go deeper into the conceptual applications. But I would never teach Simpson's rule. Not in here. Okay, so that's 4.7. Well, what happened to 5.1 and 5.2? 5.1 is lots and lots and lots of applications. Consumer and producer surplus, so having too much of something or having not enough of something. Price floors and price ceilings. So a lot of people say, hey, you're supposed to produce at an equilibrium point where supply and demand meet, or marginal revenue and marginal cost meet. There's a couple different ideas behind that we've gone lightly into. But there are some things in the real world that sometimes make it a little different than what you might expect. You might have price floors or price ceilings. Like you might have the government saying, no, you can't make this item any more expensive because then it's just going to make it out of price for your average consumer, and the consumers need this to live. So hey, you can't charge more than $4 a gallon for non-GMO milk, or sorry, for GMO milk. Non-GMO is more expensive. So a lot of price ceilings involved when we talk about food, when we talk about crops. Price floor is kind of the opposite idea, where you want to charge a minimum cost no matter what, even if your equilibrium point is, say, maybe, hey, you should sell this item at $5, but maybe there's just a reason you have to sell it at $7 no matter what. Maybe you're trying to maintain product integrity. a lot of people will say that if you, so let's say you have a item that costs $5 originally, and then you say, hey, well, let's make it $4 because our profit margins will still fine because we're selling it cheaper, demand will increase, more people are going to want it. And that's usually true, but there are some markets, usually like high-end quality markets, where if you don't charge enough, consumers actually think that the product is crap or garbage, and then they won't buy it, even though it's the same product. There are tons and tons of things in the world that you have, let's say maybe some Ray-Bans sell for $100, and you'll have 1,000 people buy this particular pair of Ray-Bans. But then the company says, well, you know, it only costs us $3 to make it, and that's probably not even that much. It's probably like $2. Ray-Bans are ridiculously cheap to manufacture. Glasses are ridiculously cheap to manufacture. There is a giant, just massive problem with that whole set of corporations that we're not really going to dive into, but they're charging way more than they really have to make money because they can. So anyways, let's say these $100 Ray-Bans, all of a sudden you charge $75 for them because you'd expect demand to go up. Well, maybe because it's a, quote, quality product, maybe all these quality product purchasers will say, well, why did it go down to $75? Obviously it's crappier. Obviously it's cheaper. I'm not buying that anymore. Now, is that true for Ray-Bans? Maybe not. I'm just trying to give you an example. If you go into like high-end wines, when you're talking about spending thousands of dollars on a bottle of wine, maybe, I've heard of examples of that where a company dropped their price by a significant margin, and you'd think, hey, that's going to make more people buy it, and less people bought it because they just have these bougie expectations, and if you drop the price, you're expecting lower quality. Now, again, that's high-end products, not necessarily staples. If you drop the product of milk 50 cents per gallon, nobody's going to stop buying it. If you drop the price of bacon by a couple bucks per pound, your teacher's going to be really happy, as well as lots of other Americans, and you'll have more people buying. But again, there are certain products, there are certain classifications of products where you need a minimum price, a price floor, even though the math behind it, equilibrium price is lower, you still don't want to go under that because the consumers are just a little weird and yeah, nope, too cheap, not buying it anymore. It's the same thing. It's still fine. Nah, they had to have dropped the price because of the quality. No, come on, man. It's the same. Nope, I don't trust you. And, you know, sometimes it is because of drop of quality. Not always, though. So that's the main idea of 5.1 and the math behind it. And it just comes into kind of an area between two curves idea. Check out your textbook. Look into it. I'm still kind of deciding. I am going to get the time to cover one more topic next class, and I'm deciding what I want to pull from. But the graphs in this section, I mean, they get really, really wacky. Like, if you look on page 476 of your text, which it'll take me 10 minutes to pull up, so I'm not gonna. I wish I'd done that ahead of time. You have this orange section of area that they call consumer surplus. They have this light blue section they call dead weight loss. They've got producer surplus labeled in green. They have a price ceiling and an equilibrium point in one example, then a price floor in another, where the consumer surplus is much smaller due to the price floor. There's a much larger producer surplus due to that. And the dead weight loss is a little bigger. And there's all these little conditions, and it's just a lot of little detail that, while again, we are an application course, that is a bit heavy-handed in application for all these little conditions on how to find surplus, how to find dead weight, how to find producer versus consumer surplus. I meant to say that earlier. That we don't ever get to use anywhere else. I just don't think it's necessary. If this is an economics class, I teach it all day. It'd take us 2 days to teach it probably. All right, so what's in 5.2? 5.2 is integrating growth and decay models. This is actually getting back more into that numerical side of things here and there, but it also then gets into talking about revenue streams and accumulated present values of money on a continuous growth model. I actually think there's some weaknesses in there. They use continuous growth models, whereas, I mean, most things aren't growing continuously in the finance world. They're growing daily. So it's not bad. The difference between daily and continuously in terms of an area approximation are not very far off, probably less than 1% error. But I still don't like that they do it that way, given that when I was actually looking at real world examples into this a decade ago, I never saw people using continuous models. I saw daily models, and it's a much uglier formula, which is why that's why I know they use the continuous models here, because it's a prettier formula. But again, lots of applications that take a decent amount of time to get into that I just don't think we have the time for without just kind of brushing off a lot of greater detail. So we're going to go straight into 5.3, which is improper integrals or improper integration. Now you might think, okay, well, we've been doing proper integrals and now we're going to teach you improper. Improper means wrong, right? Well, think about math a little more carefully. Yeah, in the real English-speaking world, proper and improper are kind of right and wrong. And, you know, right and wrong are loose words to say there. I think better and worse. It's like when you put your elbows on the table. You know, proper would be not to put your elbows on the table while you're eating dinner. Improper would be to have your elbows off the table. But then you hear a doctor come in and say, well, actually, if you've got carpal tunnel or if you've got cubital tunnel, it would be more proper for you to have your elbows on the table, because if your arms are pressed on the table, your forearms are pressed on the table, you're cutting off your blood flow and you're making your tunnel situation worse. So I think that's a little ironic. Elbows on the table while improper is better for your body, especially if you have those particular issues. But in math, proper and improper don't mean the same thing. Think back to fractions. A proper fraction was a fraction that was less than 1 whole, and an improper fraction was greater than or equal to 1 whole. So like 2/3 would be a proper fraction, but 3/2 would be improper. It's not that improper fractions are bad. It's just a way of classifying them. I bet if we were naming those in 2020, proper and improper would not be the terms associated with them. Just like we call radicals things with square or cube or whatever roots, or rationals or fractions, or calculus, again, outside of mathematical thinking, is junk between your teeth. It's more of a dentistry term. When we talk about the term differential, that's got a lot of different meanings. In the medical world, you talk about a differential diagnosis. In the car world, you talk about differential being part of your suspension. You get a lot of people in the real world that want to use the word differential when it's just difference because they want to sound fancy. I mean, I'm not going to hark on someone for using a wrong word. I use wrong words all the time. Can't be has in good English. Anyways, what is improper integration versus proper integration? It has to do with the upper and lower bounds traditionally, or whether your function is going to an infinity or not. So, improper integrals are...
Professor, we can't see your screen.
Oh no, thank you. Whoever just said that. I must have only single-click screen share at the beginning. And you know what? The little chat window, y'all been saying that for like 10 minutes and the chat window wasn't popping up. I love y'all. Thank you for catching that. And at least, thankfully, I hadn't really typed anything yet, so. Life is fun. I would much rather have this issue. I think I've said this before, but last week or 2 weeks ago, it was last week, my other class, the recording didn't even happen. I ended class and then I have this little menu that pops up that it says it's converting. That never popped up. And yeah, that was terrible. I had to re-record the class. This is a much better issue. Okay. So improper integrals are such that either the endpoint, one of the endpoints is an infinity, or function value at one of the endpoints is infinity, is n infinity. And when I say n infinity, I mean plus or minus. So improper integrals are when this function shoots up forever and ever and ever, so that's an asymptote, or shoots down forever and ever and ever. Or if we're just going to integrate from, say, 0 to infinity, or negative infinity to infinity. It's not that one of the endpoints has to be an infinity, both can be as well. So we're no longer talking about finite regions. And the first thing you think is, oh, well, if you do an infinitely long width, the area has to be infinity, right? I mean, just think about all the different integrals we've done before. So if we have, say, a quadratic, where our function looks like this, if we were going to integrate this thing to infinity, the area just keeps getting bigger and bigger and bigger and bigger and bigger. So if you integrated this from, say, 0 to infinity, this area would actually be infinity. If you did the integral from 0 to infinity of x squared dx, this would turn out to be infinity. And you can see this geometrically because as you go further to the right, the area gets bigger because the function is higher and higher and higher. So maybe up to a certain point, the area is 1,000. Just go further and it can be 10,000. Go further and it can be 1,000,000. Go further to the right and it can be 10 million. Go further to the right and it can be 1 trillion, a quintillion, a septillion, a nontillion. That's 9. 9 of those things. So the further you go right, the bigger the area is, and every time you go right, the area gets bigger and bigger and bigger and bigger, and the rate of the area increasing is getting bigger and bigger and bigger. So that's why this area is infinite. It's not really logical to find that area. But what we can have happen is, what if instead of this thing growing to the right, what if it decayed? So what if our curve looked more something like this? Now this area, got some decent area over here, and in fact this thing, this is part of the graph of 1 over x. I'll write that to the side over here. Or 1 over x squared. I don't want to say which one. 1 over x to the n, because what that exponent is will cause some issues, as we'll see and discuss. But this function, as you go wider and wider, it's getting shorter and shorter and shorter in height. It is possible. It is possible this area is not infinity. So the integral from, say, 0 to infinity of 1 over x to the n. That's what we're doing here. I'm saying maybe it's not infinity because the heights are getting smaller and smaller and smaller. So even though you'll go to infinity in width, maybe this height is shrinking quick enough that all these areas over here are so microscopic in size that they don't really affect the area. In other words, most of the area is seen in this region right here. And that all this stuff maybe only adds 1 or 2 to the final area or some small number. But believe it or not, it's possible that this thing doesn't drop quick enough. That's why I said it's possible this area is not infinite. So if the height of the function doesn't drop quick enough, which is a very loose statement, how quick does it have to drop? We can't even determine that. We just have to try and do the integral. So if the height of the function doesn't drop quick enough, then the area still infinity. Let's try the integral to see what happens. But the problem is, how in the world do you plug infinity into a function? You don't. You instead just need to know the behavior of that function at infinity. And guess what? This goes all the way back to the first week of class when we were taking limits. Sometimes we were doing the limit as, say, a function went to 5. Sometimes we were doing a limit as a function went to infinity. And we had to look at the end behavior of the function, and we classified that, based on a couple of different features, which we will reiterate those features very, very shortly. So we will need limits. To quote, plug in infinity. Again, we don't really plug in infinity. We just think about what happens at infinity. And it's usually either 0 or infinity. It usually either goes to 0 or usually goes to infinity. There are cases where they don't. But we won't be dealing with those exceptions for single polynomial terms. So, for example, if you had the integral from some starting point a, so this a would be a number like 0 in the last example, and we were going to positive infinity. And this was just some function that was given f of x dx. You would have to go and change this to a limit as b goes to infinity. We'll call b the upper limit now, and then integrate from a to b. So we won't plug infinity into the function. We'll do the integration. We'll plug in b and a, and b will literally be the letter b. But then we'll say, okay, well, if we think about b becoming extremely large, if it goes to infinity, what would happen to the term that has the b in it? Is it 0 or is it infinity? So we have to know that. So we're only able to evaluate this if the limit exists. If it doesn't exist, that means the area is probably infinity. So let's remind us of a couple of different limits as certain things go to infinity. So reminders. What is the limit as x goes to infinity of 1 over x to the n? Where we're going to assume that n is positive. So it doesn't have to be, but there's two different answers. Whether n is positive or negative here, you get two different answers. So I'll split these into cases. When it's negative here, I'm going to write it a different way. All right, so x is the thing that's in the bottom, and this is a positive exponent, which means the bottom is going to be getting bigger and bigger. Just think about if the n was a 2. So 1 over x squared. Think about your x getting bigger and bigger. 10. 10 squared is 100. 1 divided by 100 is 0.01. All right, well, what if your x was 100? 100 squared is 10,000. 1 divided by 10,000 is 0.0001. I think I may have said one zero too few, but you get the point. If you put in 100,000 and a million, that output is just going to keep getting smaller and smaller and smaller. We did this at the very beginning of the semester. This limit was 0 because the denominator keeps getting bigger and bigger and bigger. Dividing by a bigger and bigger and bigger and bigger and bigger number makes this thing smaller. You can see this graphically. Just do 1 divided by x squared. Again, I'm picking a particular n, but the bigger you make n, the more obvious this becomes. See, look at this. As your n gets bigger, this thing just goes to 0. It goes to 0 very quickly, in fact. Trace. All right, it's at 1. Then it's at 0.15 by the time you get to 3, 0.01, 0.02, 0.011, 0.009. I mean, it's going to 0. We've done this stuff before. Hold on. Okay, had to cough there. All right, limit. What if it was the other way around? What if it was the limit as x goes to infinity of x to the n, where n is positive? This is basically flipping the script on the previous case. So I'm only trying to think about positive exponents here because numerically that's the only way we can think. When we see negative exponents, we just flip them around to do calculus or to make the algebra clean. So that's why I'm not trying to think about these with negative exponents. But this right here, this x to the n with n being positive, that would have been 1 over x to the n with n being negative. So again, this second case right here is the first case, but just flipping the direction of the inequality here. So what if we had an x squared or an x cubed? What happens as x gets bigger and bigger and bigger? Well, let's just go to x squared. If you plug in 10, that squared value is 100. If you plug in 100, that squared value would be 10,000. If you plugged in 1,000,000, that squared value would be 1,000,000,000,000. This thing gets bigger and bigger and bigger and bigger and bigger. This limit, you could either say is infinity, or much preferred to me, does not exist. Now, I actually have to make a special memo here. I forgot to mention, also the n can't be 1. If it's 1, actually I take that back. No, it doesn't. Even if it's the first power. So those are our polynomial terms. This is something that you should be really familiar with, in my opinion. You might need to dust it off, but we did talk about these very heavily in the beginning of the semester. But you'll also see this stuff come up with exponentials and logarithmic terms, so we need to consider them as well. So what if we had the limit as x goes to infinity for e to the, and I'm going to write this one. I know I just said we don't like to think about it this way, and so I didn't on the left one. But really, we don't like our exponential terms in denominators for calculus, so this is the better way. And I have to say that a is positive here. And I don't want to write it right there. Actually, yeah, it's fine. So this is a positive number, meaning that the coefficient is negative here. So as x gets bigger and bigger and bigger here, this exponent's going to get smaller and smaller in terms of negatives. So if you plug in, say, x is 100,000, let's say the a is 1. So this is now e to the negative 100,000, which means you have to do 1 over e to the positive 100,000. And that falls in line with this. You're going to be dividing by a really, really big number, which makes this a very, very small number. This limit ends up being 0. If you don't trust that, calculator, let's just do e to the negative, and I can make up any positive a value. Let's do e to the negative 3x. Let's see what happens here. Look at that. It fell really quickly. If you trace it, by the time you're at 1.7, you're already at 0.006. And as I keep moving right, these e's just means move the decimal left that many times. So this is 0.00013. Now we're at 0.0000079, blah, blah, blah. I mean, this thing is just practically writing the x-axis. That's that horizontal asymptote we see with exponential decay functions. So that limit goes to 0. But what if there wasn't that negative there? So we're going to keep the a positive still. If this was a positive number, so now the exponent is ultimately positive, I can just delete the negative. This should be exponential growth, which we should all be familiar with. And this thing grows up and up and up, and if you trace it, I mean, by the time we're at 2, it's already at 312. By the time we're at 5, we're at 450,000. No, I'm sorry. Is that millions? That is million. 4 million and some change. Wow. By the time we're at 10, we're at 1 times 10 to the 13th. So that's a 1 with 13 zeros after it. That's a big number. So this thing is going to infinity, so we say does not exist. There are 2 words we can use with going to 0 or going to infinity. We say convergent or divergent. When we converge, that means that the answer is finite. When we're divergent, that means it's infinite. And those are very, very common terms used in advanced calculus that we're not going to get into studying, but the concept of convergence and divergence is really important when you're trying to approximate functions. So like when we're doing those rectangles to approximate the area under a curve, it's very important that those areas are close and that the more we do, the closer we get. that's an idea of convergence. If for some reason we did more rectangles and it made the area a worse approximation, which, believe it or not, can happen for weird classifications of functions, that would be divergent. And again, there's an entire field of mathematics on convergence versus divergence. All right, so there's our exponentials. What about our logarithms? The limit as x goes to infinity, and we only do the natural log in here, just like the natural exponential. Now remember, if you take the inverse of an exponential, you get a logarithm. So if you flip e to the ax across the line y equals x, you get the graph of a natural log. Remember, e to the x looks like this. And then the natural log of x, again, if you flip that across the line y equals x, what it ends up looking like is something like this. So e to the x has a horizontal asymptote on the left side. When it's growth, if it was decay, we'd flip-flop it. So the natural log has a vertical asymptote at 0. Remember, you can't plug 0 or any negative numbers into a natural log. Hence, when we integrate, we need the absolute value. But that quick growth of exponentials is instead slow growth for natural logs. But this is not an asymptote. This right here is not an asymptote, which means it's not flattening out. It is growing. It's just growing very, very slow. It's the tortoise versus the hare kind of situation. Not necessarily with the moral that the tortoise beats the hare, just in that one's growing quicker than the other, one's moving quicker than the other. So because this thing is going up forever and ever and ever and ever and ever, even though it's going slowly, it will hit eventually infinity. So its limit also does not exist. So there's only 2 of these scenarios that I'm giving you where a limit exists, and that means that you could actually find the area. So guess what? Those are the 2 most common scenarios. We are most commonly dealing with this one and with this one. That was a weird highlight. I'm not saying the others don't come up. You can most certainly get divergent areas, infinite areas. I'm just saying that because most of the answers are finite, we usually deal with those 2 highlighted scenarios. So if you're going to skip ones to memorize, I'd skip these 3 and memorize these 2. But really, if you memorize one, the other falls naturally. If this limit exists, the other one doesn't. If this limit exists, the other one doesn't. Also, if you don't trust my graph of the natural log, quick reminder, natural log of x, boom. There's that slow growth. Again, there are functions that asymptote to a specific vertical height. Rational functions, things like 1 over x minus 5, or 3x plus 2 over 7x minus 1, that one more in particular. That thing would actually taper off to a specific height. We've kind of neglected rational functions so far. That's one of the things I'm kind of thinking about discussing next class. That's one of the 3 main topics I'm probably going to circle back to. I just got to figure out which of those 3 I want to, or if I have time, maybe 2 for a lighter discussion. All right, so let's try this out. Let's see what we're doing and see where it goes. Whoa, whoa, whoa. Also, I just realized that since you didn't see my screen for the first 5 or 10 minutes, and I'll do this again at the end. Here's those notes that I mentioned. Thankfully, I said all the dates out loud. But there they are. Maybe snap a quick picture of this if you have to, or a screen grab, or just remember where it is in the lecture. But again, I'll do this at the end just like every single other time I have. At least I hope I have every single time. Okay, example 1, evaluate the improper integral. I'll just write it here. Please pay attention to how MyMathLab wants you to answer these if it is a non-finite value. Again, you will have, that looks like integral, doesn't it? There we go. Some of these will be finite answers. Some of these will be infinite. So they may want you to write does not exist. They may actually want you to write infinite, which is really rare. that a book wants you to do that. Okay, A. The integral from 1 to infinity of 1 over x squared dx. The dx could be in place of the 1 or to the side. It doesn't matter. We've talked about that many times. So this is an improper integral. How do I know? I see an infinity here. There are improper integrals that do not have an infinity in them, and that's because they have vertical asymptotes somewhere in them, if not the end, somewhere in the middle. So there are times when you'll have to do this, potentially, in all of calculus, where the limits aren't actually infinity. But all the examples I do, it will be that way. I promise. Okay. So because of the infinity, we have to change this up. We have to say equals the limit. And what letter you write here does not matter. You can do B, you can do A, just don't do X, you can do Z. So the limit is B goes to infinity. So we want to think about this number B getting really, really, really big. And we're going from 1 to B, or 1 over x squared dx. Okay. But we know how to integrate 1 over x squared. When you looked over here, it was terrifying because, oh, infinity, well, what do we do? That's got to be an infinite area, right? Right? Question mark, right? Maybe? Voice is getting higher? Okay, well, let's ignore the infinity part and let's just think about, what if this was a number, 1 to 5, or 1 to 50, or 1 to 5 million, or 1 to 5 trillion? Just think if this was a number. So now all I got to focus on is this part. I'm going to ignore the limit now. I'm going to keep writing it until I take the limit, but I'm still ignoring it basically. So this will be equals the limit as b goes to infinity. And then I don't know how to integrate 1 over x squared in this format because the x is in the bottom, but we know how to bring it to the top, make it a negative exponent. So this would be the limit as, oh, I forgot my integral symbol. 1 to b of x to the negative 2 dx. I don't need that 1 anymore because it would just be a 1 here, which is unnecessary. Now we know how to integrate this. We use a power rule. Now if that had been 1 over x, it would not be a power rule. It would have gone to that natural log with an absolute value. Spoilers for later. All right, so equals. We're not doing the limit yet, so write it. But now we're going to integrate. So we add 1 to the exponent and divide by the same value. Negative 2 plus 1 is negative 1. So that's x to the negative 1 divided by negative 1. And we're evaluating this between, there's no plus c needed, 1 and b. Dividing by negative 1 is the same as multiplying by negative 1. And because we're going to be plugging stuff in now, I don't really want that x to the negative 1 there. Let me do one thing at a time though. So limit b goes to infinity. Negative 1 times x to the negative 1, evaluated from 1 to b. So again, that's just me bringing the negative 1 from the bottom to the top, changing from a division to multiplication. If that had been a negative 5 or something, the 5 would still be in the bottom, but the negative could be in the top. But I don't know how to evaluate negative exponents. So this is the limit as b goes to infinity for negative 1 over x to the positive 1 now, evaluated between 1 and b. Now we can plug in the upper and lower limits. The upper limit is the b. We're not taking the limit yet. So limit as b goes to infinity. We're back to that stuff. I know it's frustrating, but you have to write it every time or you might forget it. And then you just leave your answer with a b. So negative 1 over b, that x is now a b. Then a minus to actually show the subtraction upper minus lower limit. And now we're plugging in 1 here, but that's another negative. So minus negative 1 over 1. This is the limit as b goes to infinity of negative 1 over b plus 1 divided by 1 is 1, so 1. We are now at the point where there's no more math to do. This is where we should be plugging in b. Now that b is in the bottom, and it doesn't have an exponent written, so it's a positive 1. And we said earlier, now we use x's instead of b's. It doesn't matter what letter this is. If you have 1 over something with a positive exponent, when you go to infinity, it goes to 0 because the bottom is going to get bigger and bigger and bigger, which makes the whole thing get smaller and smaller and smaller. Dividing by a bigger number makes this whole thing smaller. So this ends up being like 1 divided by infinity, and 1 divided by infinity is 0. Or again, just thinking as this goes to a million, a billion, a trillion, this division goes to 0.1, 0.01, 0.000000001. It's going towards 0. Negative 0, which is still 0. This plus 1 here, though, stays. There's no limit to take with a number. It's just when the variables are there. So there's a plus 1, and 0 plus 1 is 1. That says that the area under the curve 1 over x squared with an infinitely long width going from 1 to infinity is only 1. The first time I did that, it blew my mind, or whatever similar polynomial term my calc teacher did. That is crazy. The area under this curve that is infinitely wide is only 1. So what I'd like to do is, using our calculator, let's put that function 1 divided by x squared up here. Let's graph it. And actually, I don't need the negative, so I don't need the left half of this graph, just the right half. So let's go with an x minimum of 0 and an x maximum of, say, I don't know, 100. Let's start smaller, 50. For the y scale, it's all positive, so let's go from 0 to, and we'll keep it small, 5. So this entire graph is over here. And it's getting infinitely high the closer you get to 0. It does have that vertical asymptote feature. But it shoots down to pretty much 0 really quickly. If you trace this, if you start at, say, 0.1, you're at a height of 100. When you go to 0.5, you're at a height of 4. When you go to 1, you're at a height of 1. When you go to 10, you're at a height of 0.01. When you go to 25, you're at a height of 0.0016. So these heights are very, very small. So there's very, 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 very small heights, or at balance are very, 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 very wide widths. All right, so let's go to the calculator section, and let's do 7. That's the integral. Let's just do the area from 1 to 10. So lower limit of 1, upper limit of 10. It was that little shaded region. Look at that, it's 0.9. 0.9. So let's make a little note here. I thought I hit blue. The integral from 1 to 10 of 1 over x squared dx is equal to 0.9. Now, this curve never goes under the x-axis, which means we are only adding to the area as we move on. What that means is 90% of the area of the curve we originally found is just between 1 and 10. The other 10% goes from 10 to infinity. All right, what if you get one, instead of going 1 to 10, let's do a different area. Let's do 1 to 50, since I have 50 up there. I think that's the wrong thing. So lower limit of 1, upper limit of 50. Let's see what this area is. So another 40 more in terms of width. And it's crunching, 0.98. 0.98, and I'm going to round that to 0.98. So 1 to 50 of 1 over x squared dx is 0.98. So 98% of the area of this infinitely wide shape is between 1 and 50. That is because that 1 over x squared function is dropping so quick that from 50 to a million, a billion, a trillion, a quintillion, whatever, is practically nothing. It's only 0.02 at best. You know what's weird? I don't have an example written that I thought I did on my notes. I'm going to do it anyways. So I love the comparison. And you know what? I think I do it just on the board anyways. I don't have it in my notes, but I still always do it. I'm talking and y'all don't even need to hear it. B. We're just going to call it B. The integral from 1 to infinity of 1 over x dx. Now I'm going to go ahead and spoil this. Because not this part, but in regards to the previous part. If I did 1 over x cubed, you'd get an answer. If I do 1 over x to the 4th, you're going to get an answer. If I do 1 over x to the 5th, you're going to get an answer. The bigger the exponent in the bottom, the quicker this function goes to 0. The smaller the area will be. So if 2 works as an exponent in the bottom, 3 is going to be even better, 4 is going to be even better, 5 is going to be even better, a million is going to be even better. But I'm not going bigger in the exponent. I've gone smaller. I've gone to 1 over x to the first. So x squared, as well as any higher exponent, would work in the bottom to get a finite area. But let's try this one. So because of the infinite limit, we got to switch this to because of the infinite endpoint, we got to switch this to a limit as b, or whatever letter you like, goes to infinity, from 1 to b of 1 over x dx, which clearly we need to make that the limit as b goes to infinity, 1 to b, x to the negative 1, if you want to. Really, I wouldn't do this. Me personally, I would have never done this because I know my rules. But this is just kind of a, hey, maybe you've forgotten a rule. This is what you might try to do, since we just tried the same thing. If you add 1 to this, negative 1 plus 1 is 0, and you divide by 0, nope. Remember, that's the one and only one version of the power rule we can't do. Remember, you can't power rule this. This was the natural log case. Remember, the integral of 1 over x dx, or if you wrote it this way, x to the negative 1, is the natural log of the absolute value. So while you can't power rule this, I'm not saying the integral you can't do. You can. We've done it many times. It's just the limit as b goes to infinity of the natural log of the absolute value of x from 1 to b. Now you might say, I know I'm plugging in positive values so I can drop my absolute value. That would be okay since we're doing an area. That would certainly be fine. All right, so this is the limit as b goes to infinity. I will leave it, though, to be technically correct. The natural log of the absolute value of b minus the natural log of the absolute value of 1. The natural log of 1 is 0. Please never, ever forget that. The natural log of 1 is 0. So the second term is gone. It's just 0. So this is equal to the limit as b goes to infinity. The natural log of the absolute value of b, and that's it. Again, that's a minus 0. This part is nothing. It's minus 0, so it's gone. Well, let's think about actually plugging in our b now. If we go to infinity, if we plug it in here, what happens? So again, you've got to think about what the natural log graph does over time if you haven't just blatantly memorized it. The natural log graph grows but slowly, but it still grows forever and ever and ever. We said earlier, the limit of a natural log as x goes to infinity does not exist. So this does not exist. It is not a finite area. I love the comparison between these two problems because 1 over x squared does have a finite area, and it's in fact a tiny number as what you might think it is. You'd probably think, well, even though it's finite, it's probably like a million or something. Nope, it's 1. But on this one, 1 over x, which again, the shape of the curve is very similar to 1 over x squared. One of the left side's reflected, but we don't even need to worry about that because this doesn't use the left side of the axis, the negative x values, that is to say. But it flattens out slower. So let me just delete the exponent from this. And let's go back to a window from 0 to, I don't know, 10, and a y from 0 to 5. This right here is the 1 over x. This right here is the 1 over x. I'm going to put the 1 over x squared up to compare visually. So now it's drawing the 1 over x squared. See, on the left side, it's actually a little higher on the left side. This right here, if I hit trace, I'm already on the left side. No, I'm not. Let's go to 0.5. Right now I'm on the 1 over x graph, which is this one. If I hit up, I go to the 1 over x squared graph, which is a little higher. At 1, they match. 1 divided by 1 is the same as 1 divided by 1 squared. And then after that, they flip-flop. Remember when we talked about area between two curves? So if I did the area between these two curves from, say, 0 to 4, you'd have to split up the intervals because one of them is higher left of 1 and the other is higher right of 1. But anyways, as you move right So I'm moving along the 1 over x squared graph, and this is covering it, unfortunately. So let me just change the y values from 0 to 1. So we're really going to focus on just 0 to 1 on the y's. There's 1 over x. There's 1 over x squared. Now you can really see that 1 over x squared is definitely lower. Again, I'm now on 1 over x squared. It's lower. So 1 over x squared, the heights of those infinitely many rectangles, is getting very small very quickly. I mean, it's almost to 0 by the time you hit 5. And look at the height. It's 0.04. Let me go to 10. 0.01. So it's 0.01, 1/100th, whereas on the other one, it's 0.1. So this one is 10 times shorter in terms of height, and that effect is going to keep compounding as you go right, and as you go right, and as you go right. So it's just funny because the area under the x squared graph is finite because it drops super fast. But 1 over x, it still drops, but not fast enough for this area to converge if you're going to go to an infinite width. All right, let me get rid of the 1 over x squared. Let's go back to that normal window from before with a y maximum of, say, 10. Actually, we did 50 the first time, so let's go to 50. So, second, calculator. Let's go to the integral. Lower limit, let's do from 0 to 10. 0, enter, 10, enter. Oh, I went from 0 to 10, didn't I? I meant to do 1, and I'm going to break the calculator because it can't handle it. It's, see, break. That's because going to 0, you have that divergence issue as well with 1 over x. I got to go from 1 to 10. There we go. And that area is 2.3. So more notes. The integral from 1 to 10 of 1 over x dx was about 2.3. The integral from 1 to 50 of 1 over x to option 7 from 1 to 50. What happened? Lower limit 1, upper limit 50. Is my window off? Oh, my x max. I have my x maxes and y maxes swapped. The x max was supposed to be 50. The y max was supposed to be 5. Sorry. Okay, now it'll work. It didn't mess up the first integration. It just wasn't letting me do the second one because it wasn't wide enough. Lower limit 1, upper limit 50. There it shades it. And it's 3.9 roughly. The fact that we went from 2.3 to 3.9, changing from a width of 9 to 49, is a clue that this is what we call divergent, especially if you compare it to the previous example. Look at how close these are to each other, 0.9 versus 0.98. By making a much wider integral width, the area value didn't really change that much on the initial part. But here, doing so, now that's still not like a giant change, but it is enough to say, I don't know, if I went to infinity, if I haven't already done this calculation, this is a clue to me that it's divergent. It's not a guarantee, it is a clue. So this bigger gap says that area is probably divergent if you went to infinity. The smaller gap says it's probably convergent. And again, convergent means the number exists, it's finite. Divergent means it's infinite. You can't really think about an infinite area, which is why we just say it doesn't exist. If we were talking about an application, that would mean we're making infinite money or something like that, or there's infinite people. Those don't happen. All right. So again, I love this example. And this is actually the largest unacceptable value of an exponent. And by unacceptable, I mean when you want to get a finite area. If this exponent was 1.000000001, this would actually become a finite area. with the x in the bottom, with an exponent of 1.0000, and I can say 0 all day long, 1.000001. All I got to do is have an extra 1 somewhere after a trail of zeros. It would no longer lead to a natural log when we integrated. It would be a power rule. The x would still be in the bottom no matter what. And because of that, when you go to infinity, the 1 over x goes to, or 1 over x to whatever power it is, 1 over x to the 0.00001 would go to 0. So this is like the worst case scenario for a polynomial type term in the bottom. Any polynomial terms in the top, they're automatically divergent. All right, well, what about radical terms? We haven't done too much integration in class with these, but we did plenty of derivations with them, derivatives. So you should still know how to handle your fraction math. They've been in the homework. What if you had the integral of 1 over the square root of x dx? I'm sorry, that's d. Pardon me there. This is supposed to be 1 over the cube root of x to the 4th, going from 1 to infinity. So you know what the next example is. And then dx, of course. And again, to the side or in the top. Well, there's an infinity. And by the way, these can be negative infinity as well. You would just say take the limit as maybe a goes to negative infinity, or b, or whatever letter you like. We just tend to use b to denote an upper limit and a to denote a lower limit. All right, so let's limit this thing. The limit as b goes to infinity, integral 1 to b, 1 over the cube root of x to the 4th dx. There are two major issues with this integrand, that is the function inside of the integral. First being, we don't like to see radicals. We need to convert them to rational exponents. So as a reminder, for about the 10th time I've done it in here, the mth root of x to the n is x to the n over m. So this is really x to the 3/4 in the bottom. I forgot to switch to red there. Limit b goes to infinity, integral 1 to b of 1 over x to the 4/3. I think I said 3/4 the first time, and I meant to say 4/3. The numerator is the power, the denominator is the index, x to the 4/3 dx, which is the limit as b goes to infinity. We don't like the variables in the bottom to actually integrate, 1 to b, so bring it to the top, x to the negative 4/3 dx. Now we can set this up with our power rule formula. Add 1 to the exponent, divide by the same value. I will show all the detail for this one. So this will be the limit as b goes to infinity. It's a terrible looking m. No more integral symbol because I'm actually going to integrate. Add 1 to that, so that'll be x to the negative 4/3 plus 1 divided by literally the same math, negative 4/3 plus 1. I don't need a plus c because we're doing an area. But I got to show the evaluation between the lower limit of 1 and the upper limit of b, which is eventually infinity. What's negative 4/3 plus 1? Negative 4/3 plus 1 is negative 4/3 plus 3/3, which is negative 1/3. Fraction math never goes away. So limit b goes to infinity of x to the negative 1/3 divided by negative 1/3, evaluated from 1 to b. Remember that dividing by a fraction is the same as multiplying by its reciprocal. Dividing by a fraction is the same as multiplying by the reciprocal. In other words, a over b divided by c over d is the same thing as a over b times d over c. If you need to take the intermediate step, you switch the big division bar, sorry, the big fraction bar to a division symbol, then flip and multiply. So dividing by negative 1/3 is the same as multiplying by negative 3/1. Limit b goes to infinity. Negative 3/1 times x to the negative 1/3 evaluated from 1 to b. Clearly, we don't have to show the 1 in the bottom. 3 divided by 1 is 3. But now that we're getting to the point where we want to start evaluating these, now we don't like this version anymore. We can do the math with this version, but nobody thinks in this way. We all think in radicals, but we have to change and do computations with rational exponents. So now let's bring the negative to the bottom. Let me just kind of do it here. So that's the limit as b goes to infinity. Negative 3 over x to the positive 1/3, evaluated from 1 to b, which is the limit as b goes to infinity of negative 3 over the cubed root of x, evaluated from 1 to b. We're finally getting somewhere. I'll give you a few seconds to catch up. Okay. See, the denominator was a 3, that's why the index is a 3. The power was a 1, that's why this power is a 1, but we don't write powers of 1. All right, we're finally ready to no longer write limit. We're going to plug, well, I mean, sorry, after this next step. One more step. We'll finally be ready to not write limit. So limit, b goes to infinity. And again, this could be a negative infinity if that was how the integral is set up. So negative 3 over the cube root of b minus, so that minus is the upper limit minus the lower limit. Now let's plug in the lower limit, we're plugging in the 1. Now this whole thing's a negative, so make sure you have that extra negative. Negative 3 over the cube root of 1. Well, the cube root of 1 is 1, so this whole part is just negative 3, but a double negative makes it a positive. Limit, b goes to infinity. Negative 3 over the cube root of b plus 3. This is finally the point where we will no longer write limit. We are finally going to think about what happens as this thing, this b goes to infinity. What happens to the over a cube root? Now, it doesn't look like it anymore, but remember, this was an x to the 1/3. So this is really b to the 1/3. So just as a note, this is b to the 1/3. If you need to see it the other way, here's the alternative version. Again, it doesn't matter which way, you can make the same analysis, but you might have an easier time with this one. What did we say happens if your variable's in the bottom with a positive exponent as you go to infinity? What happens? This thing in the bottom gets bigger and bigger and bigger. It gets bigger very slow because it's a cube root. But cube roots have that same kind of shape as a natural log on the right-hand side. A little quicker growing, though. So this will get bigger and bigger and bigger. We're taking a cube root of a number. A cube root of 8 is 2, a cube root of 27 is 3, a cube root of 64 is 4, a cube root of 125 is 5. So I have to get bigger and bigger and bigger to get an answer that's bigger. So I'm going way, way bigger on the independent variable to get a bigger value on the dependent variable, but they always do get bigger. So as the bottom goes to infinity, dividing by infinity becomes 0. So this bit right here goes to 0. When it's infinity, in the same way that 1 over x went to 0, or 1 over x squared went to 0. So this is 0 plus 3, which is 3. Again, a surprisingly small answer for an infinitely wide amount of area. Maybe you're curious what that function looks like. So let's pull up our calculator. That was 1 divided by the cube root. I got to go into here to find that. There's my cube root. If you need any other 4th, 5th, 6th roots, whatever, that's this option. You would type the index, then that option. And then That was the cube root of x to the fourth. Look at how similar this kind of looks in the same window as that, that 1 over x before. It kind of starts pretty high up over here, but it flattens out quickly and quickly and quickly. Now, maybe it's flattening out quick enough to have a finite area, maybe not. Well, we showed that it was. The calculation was sound. Let's do that integral test and just see what happens from 1 to 10 and 1 to 50. I won't write them down this time. So lower limit of 1, enter. Upper limit of 10, enter. So from 1 to 10, this area is 1.6. Let's just go with 1.6. If I went from 1 to 50, though, so 1.6 versus it's taking a little longer because it's a complicated function. 2.2, 1.6 versus 2.2. So that's a gap of 0.6. That doesn't give, a gap of 0.6, you might say, well, hold on. When it was a gap of like 0.1, that was okay. When it was a gap of 1.6, that was too much. This is 0.6. I don't know. I mean, it is completely arbitrary. Some people might say, well, that makes me think, since it went from 1.6 to 2.2, with an increase of 0.6 in area, maybe that's going to converge, maybe it's diverged. Maybe that's not enough to tell. And that's why I'm doing this. I don't know that that's enough to tell just by looking at the numerical analysis side of things. But again, when you do the calculus, when you do the formulas, it does turn out that this area is 3. So if I really wanted to take like 15 minutes, I could make this thing as like 1,000 wide and just let it crunch and crunch and crunch, and it would still be less than 3. So if going from 1 to 10, the area was 1.6. Going from 1 to 50, the area was 2.2. Going from 1 to infinite, it's 3. So it's got another 0.8 to pick up from 50 to 1,000,000. And again, I could, on my own time, do that, but this function, you saw how long it took to crunch up to 50. Imagine this thing trying to do those rectangles or whatever in its own brain going up to 1,000. It would take like 10 minutes, but what you might want to do is download a TI-83 if you don't own one. Make the window from 1 to 1,000 and do what I just did, what I talked about. And I bet that area would probably be like 2.6, 2.7. I mean, that's just a guess. All right, now let's do D, the one we started writing earlier. The integral from, and let's just change the lower limit, no particular reason besides just to have it different. From 4 to infinity of 1 over the square root of x dx. Now your first instinct is probably going to be, after seeing that last problem, oh, this is going to be a finite area. It's going to have an answer. Let's execute and see what happens though. And you might think that because, oh, well, this last one had a radical in the bottom, so all radicals in the bottom are probably okay. Well, let's compare A and B. We saw an x in the bottom, you saw x squared in the bottom work, and you might think, oh, well, that means they're all okay if an x is in the bottom. Nope, this one is not okay. These radicals are the same thing as exponents, it's just fractional exponents, like a 4/3 instead of a 1 or a 2. So let's do all that changing. We know we got to do a limit as b goes to infinity. From 4 to b, and that's going to be 1 over x to the 1/2 dx, which is the limit as b goes to infinity. Integral from 4 to b, x to the negative 1/2. Then we can integrate it. Leave the limit. You got to leave that limit for a long time. Add 1 and divide by the same value. So what's negative 1/2 plus 1? Negative 1/2 plus 1 is negative 1/2 plus 2 over 2, which is positive 1 over 2. Interesting. So this is x to the positive 1/2 divided by a positive 1/2. No plus c needed, no dx needed. Evaluated from 4 to b. Dividing by a half is the same as multiplying by 2. We just made that argument in the last example. So that's 2 over 1 times x to the 1/2. evaluated from 4 to b, which is the limit, as b goes to infinity. That looks like a 2. Of 2 times the square root of x, evaluated from 4 to b. Now we can plug in the b and the 4. So the limit as b goes to infinity. 2 square root of b, that's the upper limit being plugged in, minus, that's part of the formula, plug in the lower limit, 2 square root of 4. Some people like to put all this in parentheses to denote the limit is talking about all of it, not just the first bit. That's up to you. It's not technically necessary though. Square root of 4 is 2, and I'm just gonna say that's 2 times 2, which is 4. So that's the limit, as b goes to infinity. 2 square root of b minus 4. Again, the square root of 4 was a 2, then 2 times the 2 in the front gave us that 4. Now that there's no more crunching to do, this is where we want to think about plugging in an infinity. Think about what happens as this goes to infinity. As b goes to infinity, what happens to the square root? Well, if you take the square root of 1,000,000, you still get a big number. If you take the square root of 1,000,000,000,000, you'll get a bigger number. If you take the square root of 10 quintillion quintillions, you'll get a bigger number. So this square root of b goes to infinity. Now, if it was in the bottom, that would be okay because 1 divided by infinity goes to 0. But this is in the top. So the square root of b, again, would go to 0 if it had been in the, let me start that over. The square root of b would go to infinity, leading to 1 over square root of b to go to 0. And in the last example, we had a cube root in the bottom. So that cube root in the bottom made the whole thing go to 0. Again, when the radical's in the bottom, if that goes to infinity, you're dividing by infinity, so the whole thing goes to 0. This radical is in the top. When your radical's in the top, you're not dividing by infinity. This thing is going to infinity. This does not exist. There is a major difference in C versus D, just like there's a major difference in A versus B, albeit at a separate time. When your variables are in bottoms with positive exponents or radicals, because they're the same thing, the limit ultimately goes to 0. When your radical or whatever positive exponent's in the top, that limit will not exist because it diverges, it goes to infinity, all the different ways of saying it. It's just interesting because the cube root of x to the 4th versus the square root of x being in the bottom and that other thing being in the bottom, they don't look that different in terms of graphs. So let's go back to more of a standard zoom. Here is your 1 over cube root of x to the 4th. Here is your 1 divided by the square root of x, the one that it's about to draw. See how it does that same kind of tapering off? It's not as steep in the beginning here, and it's tough to see, so let's zoom in. Let's make our window. Let's go x. We don't care about the negatives for this stuff, so let's go from 0 to 10, and let's put the y scale from like 0 to 3 or 4. So there's the 1 over the cube root of x to the 4th. It's drawing slowly. And now here comes the 1 over square root of x. See, look, it's the same kind of happening when we compared 1 over x squared versus 1 over x. They have a greater rate of descent in the beginning, but then a much slower rate of descent after you hit x equals 1. That's their crossing point. So the 1 over 1 over third root of x to the 4th, it gets close and close to 0 quick enough that all of these little rectangles, those infinity rectangles going to infinity, are not really going to matter much. This one does not approach that axis quick enough. It's all about how quick the function closes in on that x-axis, and this is not enough. And it's just so funny because there's not a lot of width here. That's not a lot of room, but it makes all the world of a difference. So what's the reason for this? Why did it happen? Why did the one thing diverge versus the other converging? It's because after we integrated with the 1 over cube root of the x to the fourth, that x term ended up being in the bottom. No matter what the positive exponent was, it was in the bottom, so that's going to go to 0 when you take the infinite limit. But with this one, because that exponent in the bottom was smaller, when you added 1 to it, it was actually enough to bring it up to a positive exponent instead of the negative exponent, so we never tossed the x back in the bottom, it stayed in the top. And plugging in infinity into anything in a top is infinity. All right, so I love those first 4 examples. A versus B, great comparisons. C versus D, great comparisons. But we need to also see, what about these negative limits, negative infinite limits? Maybe we're going from negative infinity to 0, or negative infinity to 1, or negative infinity to negative 12, something like that. Or maybe even what if we have a limit from negative infinity to positive infinity? So we can also do improper integrals involving negative infinity. So let's go ahead and get all the little notation out of the way. There's not going to be anything crazy here. If you wanted to do the integral from negative infinity up to some number, and again, we typically let b represent an upper limit of some function, f of x dx, you'd have to make this the limit. And we like to use a for the lower limit. The limit is a goes to negative infinity, integrating from a to b, f of x dx. So again, the b is a number that was probably given to you already. I say probably, I mean definitely for this format. But we can also do this. The integral across the entire x-axis, the integral across the entire real number system, negative infinity to infinity, f of x dx. So the way you have to do this is you actually have to split it up into 2 cases, these 2 cases being what we just saw. You have to go the limit as a goes to negative infinity, integral a up to some random value. I don't really want to say c, so let me just say some number, because we've been using c to represent a constant of integration. And you could say we'll just use d, and yeah, that would be fine. But let me just say, go from a to a number, so from negative infinity up to a certain point, and then your regular old function. But then you also have to do plus the limit as b goes to infinity, and then integrate from the same number you stopped at previously up to b, f of x dx. This is the same idea that we've seen dealing with an area between 2 curves where they cross. Now, these don't have to cross. Sometimes they do. In fact, most of the functions that have convergent infinitely wide areas, you end up having to split this because there's an asymptote somewhere in the middle. It's usually 0. So first of all, you would probably need to split this up into 2 limits because of that, because there'd be a vertical asymptote somewhere. Second of all, you have to set this up into 2 integrals because of the unique limit situation of which I have an error on. This a is not supposed to be infinity. It was supposed to be negative infinity. I said it, I just didn't write it, because the lower limit is negative infinity. So the limit as a goes to negative infinity, so essentially this is going from negative infinity up to, say, it's usually 0. 0 is usually where we split this, usually. And admittedly, I'm not going to test you on that, so I'm not going to do any in the notes. So go from a to 0 and then 0 to b. If the vertical asymptote was somewhere else, you'd go wherever the vertical asymptote was. Let's say the vertical asymptote was at 1, then you'd go from a to 1 and then from 1 to b, where a and b represent the negative and positive infinity respectively. But we will do an example of this first case. So example 2. Evaluate the improper integral, same instructions as before. So let's go from negative infinity up to 0. And let's do e to the 3x dx. Now, the first thing some people think when they look at this is they go, it's divergent, it goes to infinity, does not exist. Because they see e to the 3x, and they look all the way back here, think all the way back here when we were doing the 5 cases we see the most, and oh, the limit as x goes to infinity of e to the ax does not exist. You have to be very, very, very careful about that. Every single one of these reminders was a positive infinite limit. There are a couple that are different when going to negative infinity. These two are unaffected. These two are the same for negative infinity. They are unaffected. So again, you might want to write this down. I'm going to erase it after a second. These two limits, if you are going to negative infinity, are the same. The first one still goes to 0. The second one is still going to go to infinity. It's actually negative infinity though, but that still just means it doesn't exist. These two are the same if you go to negative infinity as they are for positive infinity. These are different. First of all, the natural log is not defined for non-positive numbers. So there is no negative infinite limit for a natural log of x. There isn't even one at 0. So that one is different. These two actually flip-flop because of the negative in the exponent. So if you plugged a negative infinity here, those two negatives would cancel out. And now you've got a positive exponent. So now it would go to infinity. If you plug in negative infinity here, there's now a negative in the exponent, which means this thing goes to 0. So I'm going to write that note down. I'm just not writing it up here. So again, if you're thinking about a limit as x goes to negative infinity, it doesn't exist for the natural log because you can't even go past 0 in terms of left. These two things are the same. These two flip-flop. So first, note. The above limits are a little different negative infinity. The polynomial, that's ugly. I'm just going to have to. There we go. The polynomials do not change. The natural log will d and e. The exponentials swap, as just explained. All right, so let's get to the work. Equals. I see an infinity, so I got to introduce a limit. As not b, a. I can use b, but I want to be more appropriate. As a goes to negative infinity, and I won't forget my negative this time, e to the 3x dx. So this will be the limit as a goes to a negative infinity. Well, this is a nice simple integrand. We have a rule for that. It's e to the 3x divided by 3. There's no plus c needed because we're evaluating between, oh, I forgot my integral symbol. Geez, from a to 0. So we're evaluating from a to 0. I got so focused on the negative part of the infinity, I forgot my integral symbol, but we got it in the end. Okay, so we're going to plug in the 0. Leave the limit. Limit a goes to negative infinity, e to the 3 times 0. Then we're subtracting off the lower limit. And now this will be e to the 3a. And then both of these are also divided by the 3. Don't forget that. I thought about writing it all over just one single 3, but I changed my mind. Let's keep it split. So the first one was plugging in the 0. This was plugging in the a, which is arguably negative infinity. Well, 3 times 0 is 0, so that's just e to the 0, and remember, e to the 0 is equal to 1. So this is the limit as a goes to negative infinity of 1/3 minus e to the 3a over 3. Now we got to think about what happens as this goes to negative infinity. And again, exponential terms, if this was going to positive infinity, this thing would diverge. If this was going to positive infinity, this is going to be like e to the 10 billion, which is so large of a number I can't even think about it. But we're plugging in negative numbers, so this is like e to the negative 10,000, e to the negative 20,000, e to the negative 30,000. And when you have a negative exponent, you flip it, so now you're dividing by a really big number, which makes it really, really small. This is 1/3 minus 0. The limit as a goes to negative infinity of e to a positive term is actually 0, because e to the negative infinity will go to 0. 1/3 minus 0 is 1/3. There we are. If that confuses you, what you can do is just swap the sign of the a. Just take, instead of having the negative here, just give it with your a. So some students do this. They go limit as a goes to negative infinity of 1/3 minus e to the 3a over 3. We do the same thing as the limit as a goes to positive infinity, but that switches the sign of the a, which switches the sign of the exponent, so that would be 1/3 minus e to the negative 3a over 3. If you want to remove the negative from your infinity, you have to throw in a negative with your variable. It's cool that that works. Whether you like to do that or not is up to you. I'm just giving you options, because then you don't have to memorize the fact that the negative infinite limits are different for some functions and not for others. And it all has to do with their graphs. Let's just go back and look at the standard zoom so I can see the left and right sides again. And I also don't want to see both of these functions. Well, I guess it's fine. Here's the 1 over x squared. Look at this. On the left side, it flattens out to 0. On the right side, it flattens out to 0. Then here should be the 1 over square root of x. I said 1 over x squared, I think. That was 1 over the cube root of x to the 4th originally. It flattened out to 0 on the left, it flattened out to 0 on the right. The 1 over square root of x is doing the same thing, even though you can't see it. If you have 1 over x cubed, or 1 over x to any power, any positive power. Look at this, on the left and right side, they both flatten out in the same manner. It flattens out from below on the left and above on the right, but it's still flattening out to a height of 0. That's why those 1 over x to the ends have the same conditions whether you're going to negative infinity or positive infinity. But when you have your exponential terms, your e to the x's, they do different things on the left side and right side. On the left side, it decays, it flattens out to 0, but on the right side, it grows. E to the negative x, it does the exact opposite thing. See? Grows on the left, flattens out on the right. So exponentials have different limits left or right-sided. When we do the natural log of x, it doesn't even have any graph on the left side. You can't go past 0, you can't even use 0. So there is no limit to negative infinity because the function doesn't even exist anywhere close to it. But on the right side, it goes up very slowly, but it does go up forever and ever to positive infinity. So you have to still maintain a basic understanding of these three core types of functions. Your polynomial types, which also gets to include radicals, thankfully, your exponentials, and your natural logs. You know what? This next section is super, super short, so we can go ahead and cover it. I was starting to think I might not want to, but I definitely do. And is it 6.1? Is that what I said? The later sections in Chapter 5 are nowhere near anything we need to do, except 5.7 differential equations are really nice. We're going to go into 6.1 next, though. I'm kind of terrified to open up a new document. I'm just going to do it here. No space, yes. I'll fix that later. I have functions of several variables. What does our textbook call it, though? Functions of several variables. Perfect. Same title. Sometimes they switch title names between text editions. I think I've said this before, but my notes are based on an old edition. My handwritten notes that I use, like where I got my examples and stuff. Functions of several variables. We have dealt with functions of several variables only a handful of times in this class. We handled them with implicit differentiation, where you had to use that chain rule concept, and like, let's say you had x's and y's, and you were supposed to find dy dx. When you took a derivative of anything with an x, it was just normal, but when you took a derivative of anything with a y, you had to throw that extra dy dx, because we're considering that y is a composite function of x, even though we don't have it. So that was very interesting and honestly much more convoluted than what's in this section. 6.1, functions of several variables, is just about how to evaluate functions of several variables, how they appear. And it's honestly nothing crazy. Instead of just f of x, you have f of x comma y. So a single variable function would look like something like this. F of x equals, I don't know, x squared plus 7. A function of several variables, or a multivariable function, so it's going to depend on multiple letters. X is no longer the only input. When we have function notation, all of our inputs need to go in these parentheses. So you actually go x comma y or x comma y comma z, depending on what letters you've got. So this might be something like x squared plus y squared. This could be like an equation of a circle if this was equal to a constant, if this was always equal to 1 or 5 or 12 or 25 or something like that. Right now, it's not a circle. Evaluations are extremely simple. To evaluate, pay attention to where the number is a sign. So that previous one, if I said, I want to know what f of 2 comma negative 40 is, I'm telling you the x is 2 and the y is negative 40 based on the placement of the numbers. So it tells you what to plug in for what number. I mean, honestly, that's it. That's the entire section. That's 6.1. Let's do some examples, though. And because it's such a simple idea, I'm only going to do a couple examples. Example 1. Evaluate as prescribed. I'm going to write Rx, prescribed. For A, we got f of x comma y. And let's go with the one we saw above, x squared plus y squared. And let's find f of 1 comma 9. So x comma y, we like these to be in alphabetical order. They don't have to be. I could do f of y comma x, but you're not going to see any mathematicians or scientists writing it that way, honestly. It's just lazy, not paying attention, not conforming, if you will. But it's not wrong, it's just weird, which, I mean, that's okay. You're just going to confuse some people. Ooh, hold on. I woke up my dog with that cough. All right, so f of 1 comma 9 says that the x value should be a 1. So that's 1 squared. Plus, well, 1 comma 9, that says the y value should be 9. X is the first one, that's a 1. Y is the second one, that's a 9. Wow, that was insane. Square the numbers. 1 squared is 1, 9 squared is 81. Add them, you get 82. Multivariable function evaluation. I can throw this at my Algebra 1 students. And in fact, I do. I just don't give them the function notation. I would just say evaluate when x is 1 and y is 9. But that's it. That's the whole problem. We're going to end on the easiest thing we've ever done, probably. F of x comma y is equal to e to the 2y plus 3x minus 7. Now, both of these terms, I have my x's kind of individualized, just x's in this term, just y's in this term, just y's in this term, just x's in this term. They don't have to go in alphabetical order. They don't have to be just x or just y in a term. They don't have to be just x and y, as we will see in the third most complicated example, but still tolerable. And we are going to find here f of 8 comma 0. So that tells us the x should become 8 and the y should become 0. You could also have multiple variables of the same thing. So this is e to the 2y, so e to the 2 times 8, right? Right, question mark, question mark, question mark, no. Pay attention, take your time. That's 2y, so that's 2 times 0. Plus 3x is 3 times 8 minus 7. E to the 2 times 0, that's e to the 0. Plus 3 times 8 is 24, minus 7. Anything to the 0 is 1, plus 24 minus 7. 1 plus 24 is 25. 25 minus 7 is going to give us 18. Yes, you could have gone ahead and combined the 24 minus 7. I just waited till the last second to do all the basic arithmetic. And there we go, that's it. One more for the road. F of x comma y comma z. I like my z's with lines in between them so it doesn't look like a 2. You don't have to do it that way. Is equal to 2x plus 3yz minus the natural log of x. And we are going to find f of e comma 7 comma negative 2. Ooh, f of e, that's crazy, right? Don't worry about it. E is not a variable, it's a number. We like to hold the e as that number unless we can evaluate it simply, or we're dealing with a word problem and asks to approximate. Now remember, in your homework every now and then it asks for an approximation, so just pay attention. So we're doing f of e comma 7 comma negative 2. Oops. Now that tells us the x is e, so an e is going to go here. That's 2 times e. Plus 3yz, well the y is 7 and the z is negative 2. So that's 3 times 7 times negative 2, better parentheses that last one. Minus the natural log of, well wait, where's my fourth variable? Add 1, 2, 3, 4 variables, where's my fourth number? Don't need one. That's natural log of x, we said x is e. This is the natural log of e. Let's clean this up, that's 2e. 3 times 7 is 21, times negative 2 is negative 42, so minus 42. Minus, I'll leave the natural log of e alone for one more minute. So f of e comma 7 comma negative 2 is 2e minus 42. You can't combine those because they're not like terms. But the natural log of e, did I say this earlier? Maybe I did, maybe I didn't, is 1. Again, you're supposed to memorize that. That's minus 1, and minus 42 minus 1 is minus 43. So you get 2e minus 43. Sure, you can get the decimal approximation if you want, or if it asks for it. This isn't an application, and I didn't ask for it. I don't care about the decimal approximation. E is about 3. 2 times 3 is about 6. This is going to be about negative 37, somewhere in that ballpark. But I really don't care. So that will close out, believe it or not, 6.1. I would like you to read the text, not necessarily read the whole section for 6.1, but again, just look at it, kind of like I was talking about with the surplus stuff. In the text, you will see some three-dimensional graphs, which I'm not even going to try and draw. I am a horrible three-dimensional artist unless it's just a cube or a very simple paraboloid, which is a parabola in 3 dimensions. But just put your eyes on some of those three-dimensional graphs. Just take a look at the examples. I'm not asking for intensive understanding of them, but just kind of see if you can see how a 2-dimensional shape might relate to a 3-dimensional shape. So we'll call it a day there. That closes out, again, 5.3 and 6.1. So let's pull up the homework list. Make sure everybody sees it today. 5.3 and 6.1 is due in 1 week. That's the 30th. You have the previous homeworks. You know your test 3 is coming up. You know your review is posted. It is at the very bottom of your My Math Lab homeworks at the moment, but I am going to assign 5.3 and 6.1 immediately after class, so those 2 assignments will be right under it. The test will, just like the first 2, be at the very top of the assignments once it is loaded. And remember that it will open at 12:01 a.m. Friday, and it will close at 11:59 p.m. Monday. Please don't just wait till Monday to wait till Monday. Try one of your attempts sooner than that. Get on the review. Try your 2 attempts. I think I've only seen a couple students actually use their 2 attempts, which, I mean, if you're happy with your first attempt, I get it. But I am kind of surprised at how many people aren't doing that. And admittedly, if I haven't said this, I'm not going to be doing this anymore for my future students. Not that you need to worry about it, because this is usually the highest level class I teach is calculus, and you won't go to any of the further calculus sequences. But because of this whole virus situation, I was playing around with ideas to make it easier on students, but hopefully our fall students are getting more used to this. So me personally, I'm going to switch to 1 attempt and be a little more normal. I'm also going to start invoking, having to record people while they're testing, but we're still kind of getting used to everything. So I wanted to take it easy on my students this summer and just emphasize learning the knowledge and doing the best with that versus having to be under super strenuous circumstances. So I hope that you have used that as an opportunity to do well. And if you are a business major, you're going to see some of this stuff in your economics classes in the future. When you're doing your 100 and 200 level, when they talk about things like marginal analysis, they usually don't talk derivatives because they don't think you've had calculus yet. When you get into your 300 level classes, they tend to assume you've had calculus and will, find total profits by doing area under a curve, or marginal rate, marginal revenue, marginal cost by doing actual derivatives. If you're not in business, I can't really say specifically where you may see some of these concepts in the future. I can't speak for every single major out there. I can hardly speak for just the sciences and a couple of business people. All right, but I'll stop rambling. Email me if you have any questions. Thank you so much for getting a hold of my attention. I'm usually really good about seeing those chat memos pop up. I don't know if I was just in the zone and didn't see it pop up, because it's usually a little orange warning at the top. Not warning, but just a signal. I don't know if maybe it wasn't showing it today, or I just didn't see it happen. But again, thank you for giving me the voice warning that my screen was not up. That would have been terrible for you the whole time. The good thing is YouTube, no, actually I'm wrong. YouTube wouldn't have had it. Ooh, that would have been bad. Thank you for saving my butt. Love y'all. Have a good weekend. Work hard, study hard. I'll get those assignments updated right now. Take care.